The physical world is in a state of constant transformation. Water boils into steam, wood collapses into ash, and solid iron slowly decays into rust. Around 500 BC, thinkers across the globe reached a startling conclusion. The Indian philosopher Maharishi Kanad and the Greeks Democritus and Leucippus proposed that if you divide matter enough times, you eventually hit a limit, a tiny, indivisible particle. Kanad called it the parmanu, Democritus called it the atom. For over 2,000 years, this idea remained a philosophical intuition. Without a way to measure the invisible, there was no way to prove these particles actually existed. Transitioning from guessing to knowing required a mathematical proof, a way to weigh the building blocks of the universe. At the end of the 18th century, Antoine Lavoisier introduced precise measurement to the laboratory, establishing chemistry as a quantitative science. In this sealed system, even as a chemical reaction takes place, the total mass on the scale remains unchanged. This is the law of conservation of mass. In any reaction, the total mass of the products equals the mass of the reactants. Shortly after, Joseph Proust identified the law of constant proportions. He found that chemical compounds follow rigid mathematical recipes rather than forming through random mixing. Consider water. Whether you decompose 9 grams or 90 grams, the result is always a fixed mass ratio of 1 part hydrogen to 8 parts oxygen. These laws provided the grammatical rules of matter. Any theory explaining the atom would have to satisfy these mathematical constraints. John Dalton, a self-taught schoolteacher, realized that these mathematical laws required an alphabet of atoms. He proposed that every element is composed of unique, indivisible particles. Dalton's breakthrough was the concept of atomic mass. He argued that every element has a characteristic mass that dictates exactly how it combines with others. Since a single atom is too small to weigh directly, scientists had to determine a relative atomic mass by comparing elements to a standard unit. Today, the standard is carbon-12. If we imagine a carbon-12 atom as a watermelon, we can divide it into 12 equal parts. Exactly 1/12 of that mass becomes our standard unit, a counterweight to measure every other atom in the universe. Dalton's theory transformed the atom from a philosophical idea into a specific, weighable unit of information. Dalton originally designed symbols using specific patterns inside circles. Hydrogen was a dot, oxygen an empty ring, and copper a circle with a C inside. As the list of known elements grew, these drawings became cumbersome. To facilitate global research, the IUPAC system replaced them with a standardized alphabet of letters. Most symbols use the first letters of an element's English name, like H or AL. Others are derived from Latin roots. Gold becomes AU from lorum, and iron becomes Fe from ferrum. This standardization gave the world a shared, consistent lexicon for the building blocks of matter. Atoms rarely exist in isolation. To find stability, they bond together into molecules or charged clusters called ions. The rules for these bonds are determined by valency, the combining capacity of an atom. You can visualize valency as the number of arms an atom uses to hold its neighbors. If we represent an atom with a valency of 8 as an octopus, and humans as atoms with a valency of 2, all 8 octopus arms can be locked only if it holds 4 humans. This specific capacity creates the formula OH4. Valency is the syntax of matter. It ensures that only certain atomic combinations are physically possible. The crisscross method is the final tool for translating these chemical laws into a readable formula. We write the symbols in charges: magnesium 2+, chloride 1-. We crisscross the values. The 2 moves to chlorine subscript, the 1 to magnesium, giving MgCl2. This shows 1 magnesium balances 2 chlorines, creating a stable net zero charge. The shifting transformations of the physical world now align with a predictable logic. The variety of the cosmos is legible, expressed through a consistent system of mass, symbols, and charges.